Hello, this is Fundamental of Programming course CO1027. In this session, we are going to talk about recursive. Well, it's a very widely used technique in programming world, not just in this particular language, but also in other language, including Python, Java, whatever. So you just know that we are going to use it a lot in the future. And the reason why we wait up to this point to learn about recursive because it's gonna utilize the concept of function. Okay, so now what is recursive? Well, recursive is based on the concept of divide and conquer, or may I say, you try to solve the problems on computer with the main principle that you divide your big problem to smaller one. And now when you try to design a recursive algorithms, it also utilize that feature. Okay, so we try to divide your big problems into smaller one, but instead of defining the solution for the problems, we define the solution for the problems at the smaller scale, which cannot be defined anymore. Okay, and then we define the solution for the bigger problem using the smaller problems. Okay, and that's how it works. That's the principle. Okay, as you may see here, we have the example. Quite too simple for me, but it is help you to understand what it means. Well, in the first example, we have a factorial functions. As you may know, what factorial is a functions with the products of all the number from 1 to n. So you may write it this way. Okay, this is simple, right? In mathematical fashion. And well, if you take a look at this one, you may say, okay, it's too easy. I probably can use iterative solution for this. Just write a loop and I can calculate this product easily. So why bothering with the concept of recursion? Well, yes, you can try that, but you can also think of the problem in a different way by looking at it as the recursive problems, right? Here we have the basic solution where you define that the factorial of 0 is 1. That's it. Well, the basic solution, like you can no longer break the small problem into the smaller problem, right? Now, in a general sense, you say factorial of n equal to factorial of n minus 1 multiplied with n. Well, this comes directly from the formula you have over there. It's it's equal to n multiplied with the product of I run from 1 to n minus 1 of I, right? And this one is exactly n minus 1 factorial. Okay, that's it. So we call this one a recurrent equation. Okay, so recursion equation is a way to define the problem with the smallest problem along with the solution, right? And you have the general solution. This is called general solution over there. Okay, so if someone asks you, okay, should I write factorial function in recursive fashion? Well, you can, but it's not gonna be efficient. Okay, now in the second example, you can see that we have a Fibonacci sequence. Well, this one is the most popular sequence of numbers we have found in mathematics, and by definitions, the first two number is 1, right? As you may learn in the high school, the first two numbers are 1. Well, how about the rest? The rest is defined as follows. The factorial number at position nth equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Sorry, Fibonacci, not factorial. I mess up. So again, if you look at this one, you can see the first line define the basic solution. Okay, or may I say it, the base case, whatever. And the second line is general solution. Okay, is a general case. And so again, this one is the recurrent equation 2. So probably any problem that can be modelized by recurrent equation can easily solve by a recursion technique, right? So you see here we have some more detail about how to design a recursive algorithms. First, you need termination. Well, basically you say, when should I stop call recursive? When should I stop the process of calculating? Well, you should stop when you reach the basic solution or the base case, right? Well, here we have another simple example. You can see here I have the base case solution here, where the factor of 0 is 1, and here I got the general solution. Okay, as simple as it look like, this code is wrong. The reason you see here is that as n is integer, then if I call factorial not 5 but -1, then your code may run into an infinite loop, and then it will break your program. So this is not working, right? Or I may say it is unsafe. So you may either change your type of data into unsigned integer, or you may change this condition. Okay, now you may want to make the stop condition somewhere in order to stop the problem of recursions. You don't want to jump into the infinite loop, right? Just like I say here, you don't want to forget the recursive termination condition. Okay, so this is one note that you have to take with you when you implement any algorithms. Now we come to the Fibonacci function. Well, it's another simple one. Again, we define the basic solution like this one. Well, it is almost correct, but not completely, because if the index of the number I want is smaller than 0, or even is 0, then it doesn't make sense to return 1, right? That's not defined. So you may try to resolve that in some other sense, whatever. The base general solution is here, which is easy to read and understand. So what I say is, for recursive, you can see the code is very short, easy to understand, and looks elegant. But consider some other factor. This is not the way to implement a function to calculate the Fibonacci, really. As I will show you later in the demonstration, you will find out that this is not good. This is a terrible behavior, or may I say the terrible way to implement a function like this. Okay. Well, now we have some other kind of recursion. It's called indirect recursion. You may say I have function A. That function A, inside the function you may invoke a call to function B, and then the function B call A again. So it's like A call itself, but not directly, but through function B. And that is why we call this mechanism is indirect recursion. Okay, so you see here in the example we have function A is called function B inside, and then function B have a call up to function A inside. And that's how it works, right? So function A is also a recursive function, but indirect. Well, when it comes to classification, you will see that we have several ways to classify. Now we have the tail recursion. When you say tail recursion, it means the recursive call you make is the end of you put it at the end of the function, and when it happens, nothing else to be done after you call that function. It's called tail recursive. And when you have tail recursive, you can basically remove that tail recursive because you can use iterative method to solve it. Okay. For head recursion, it means you activate a recursive call at the beginning of your function. Well, it happens sometimes. It depends on the problems that you are dealing with. Okay. And very often we have the middle recursive, and we have multi-recursion also, right? And mutual recursion here means well, that indirect recursive we have just talked in the last slides. Okay. Now we talk a bit about recursion versus iteration. Why should we care? Well, sometimes recursion is better than iteration because the code of recursion is simpler, easy to understand, look elegant, and whatsoever. You can basically write that code in just a few lines of code, extremely easy. But it may take a lot for you to write the same function, the same feature using iterative method. Well, sometimes that works, but also there are cases when recursion is not so good. It's basically the terrible way to implement some functions, some features, some algorithms, because well, iteration just work better. Okay, so this is why we care. Okay. Here is some information that I put down here for you, but I believe that we have more to talk on the class, so just bear with me. We will have a discussion including with some demonstration on the class, so you understand this one better. Well, there are some notes over here for you to decide whether you should choose recursion. Well, one of the biggest issue of recursion is it utilizes the code stack, and as I mentioned in the last lecture about function, your function stay on the stack. So considering a situation when your function utilize some variable inside and that variable actually a little bit big, then if that is the case, every time you call function, the memory for that function consume some space on the stack, and you cannot call recursive indefinitely. There is a limit amount of memory for your stack, so up to some point your program will stop or break, or just crash because you don't have enough space for another core on stack. Then you turn out to get the stack overflow issues. Okay, that's how it works. Now here's another example of Hanoi Tower problems. This is very classic one, and well, I can either write this algorithm for you right now without demonstration. That's fine to me. Let me try to do it in very short code. Let's see. Let me design the function this way. The function will return nothing as I don't expect anything in return. Let me call that function move. Okay, it will take in well, should I explain about the rule of this game? Well, there are a tower. That tower consists of several disks. The size of those disks are arranged in the ascending order. I mean, the biggest disks stay at the bottom and the smaller disks stay at the top, and in that order you have to move those disks from the source tower to the destination tower. And when you move, you can only move one disk at a time, and well, you cannot put the bigger disk on the smaller disk. That's the rule. Okay, so as complex as it look like, this is really simple if you implement using recursive. Now if you think about iterative algorithms, then I would say it's really hard because there is no particular pattern for moving those disks, right? And so designing such iterative algorithm for this problem is extremely hard. But when you try to implement this one using recursive, then it's extremely simple. Now let's say I have to move and this from the source to the destination using some intermediate column. Then what should I do? Right now I have to find the base case solution. What is the base case solution? If I have only one disk, then that is the base case, right? In that sense, what should I do? Let's say move one disk from where? From the source to the destination. Okay, and yes, I would like to put some order. Yep. Okay, that's the first or the last condition. Now that's also the stopping condition for your recursive code. Now if n is not 1, which greater than 1, then you probably want to do something else. What you want to do is you are going to move n-1 disk from the source to the desk, and then you move one disk from the source to the destination, and then you move n- disk from the intermediate tower to the destination tower. Well, I can write this directly like this one. Move what? n-1 disk from the source tower to the intermediate tower using the destination as the something. Okay, then I would like to move the biggest disk, which is one disk, from the source to the destination. Now the intermediate It's not so important, so let me say I just say 0, whatever, I don't care. The last statement I need here is move n minus 1 this from the intermediate column, because it is there, right? So move from there to the destination using the source as the intermediate tower. Okay, and that's it for the else case, and this is the end of your function. Done. Nothing else to do. So you see that the whole set of the Hanoi Tower problem can be expressed in just 4 lines of code, or 5 lines if you want to call it. Anyway, it's look crazy simple, right? There are tons of problems that you can solve with recursive. Some are simple, some are complex, and I hope you take this with you, and then we may have some time to discuss on the class. Okay, so prepare your questions, and then let's see, we may have something fun on the class with this one. Okay.